Hello, my name is Jennifer Smith. I'm a lead engineer working in the Enterprise Relational Database Server group. Today I will present an overview of the new features in the Enterprise Relational Database Server Release 22R1. Throughout this presentation, I'll refer to this product as RDMS. There are 7 new features I will present today. These features fall into the following categories: new functionality, performance, ease of use, and scalability. Let's look at the features that provide new functionality. They are: allow fetch absolute and fetch relative statements in stored procedures and triggers, and to allow a view to be referenced in the from clause of a derived table or common table expression. The fetch absolute and fetch relative statements are now supported in stored procedures and triggers. The fetch absolute and fetch relative statements had previously only been supported through embedded SQL. Using the fetch absolute fetch relative statement can eliminate the need to code a fetch loop, resulting in improved performance and simplification of code. In this example, we are looking to return the value at the midpoint in the cursor's solution set. The value, row count, was calculated using the number of rows in the cursor divided by 2. In the old method, we needed to use a retrieval loop, casting aside the returned values until the record we are waiting for is returned. The fetch relative statement replaces the while loop, the fetch loop, and the increment statements, returning only the record value we want. Looking at the syntax, this SQL statement shares the definition that currently exists in section 8.6 in the RDMS Programming Reference Manual. Absolute N retrieves the nth row from the first row of a cursor and sets the current cursor position to the returned row. If n is 0, an error is returned. Relative N retrieves the nth row from the current cursor position and sets the current cursor position to the returned row. If n is 0, RDMS returns the current row. This is the same as the fetch current statement. Here we have an example where the value of n is passed as a SQL input variable to the stored procedure SPTBL. The stored procedure is called with a value of 10 for this SQL variable. The cursor is opened, the first 10 rows are skipped by the fetch relative statement, and the 11th record is returned. The subsequent 2 fetch next statements will result in also returning the 12th and 13th records of the cursor's solution set. The next feature allows a view to be referenced in the from clause of a derived table or common table expression. This feature lifts a current restriction in the derived table common table expression functionality. In this example, the derived table DT is retrieving from the RDMS catalog view table columns. Being able to reference the catalog views in a derived table is particularly useful when you must group or perform some type of aggregation on the results, and the view definition contains a group by clause or some type of aggregation. RDMS only supports nested grouping functions through derived tables. In this example, the common table expression, expensive houses, is referenced in the from clause and a subquery predicate in the where clause. It is derived from the view s1.v1_houses, where v1_loc does not equal Bloomington. This example finds all the local indexes associated with a given schema, table, and partition name. To retrieve this information, we need to search multiple catalog views. In this last example, we create an updatable view, Payment TRF Table. We are deleting from the view Payment TRF Table. The delete is performed on the records that satisfy the in subquery predicate. The subquery contains a join of the view to a derived table, days, whose result set is derived from grouping like values from the view's record set. The satisfaction of the where clause determines the set of records that are deleted. Next, we will look at the performance features. There are two performance features. Both features involve speeding up processing of predicates whose operands contain arithmetic or built-in functions. The first improvement is on where clause predicates when both operands contain arithmetic or built-in functions. The second feature expands the application of the hybrid hash join to include equality predicates with operands that have arithmetic or built-in functions and use these predicates as hash keys. RDMS has changed when it evaluates where clause predicates when both operands contain arithmetic or built-in functions. Evaluation of these predicates are now done on the data page. This means only records that satisfy the predicate are copied from the storage manager into memory for processing by the abstract machine. The old method required the storage manager to deliver the records to the abstract machine for evaluation. This change is especially beneficial when there are no records that satisfy the predicate. In this example, the left and right operands of the first predicate in the where clause are arithmetic expressions, specifically price plus 5 and max price plus 3. In this example, the left and right operands of the first predicate in the where clause are built-in functions. The column value customer name is folded to uppercase, and the result is compared against the value in the program variable $P1 folded to uppercase. The feature changes the candidate predicates from RDM predicates to RSM predicates. Therefore, the explain statement will reflect these changes when displaying information regarding predicate evaluation. The hybrid hash join method is currently not used when one or both sides of the equality predicate contain arithmetic or built-in functions. This feature expands the cases where the hybrid hash join can be used. Hybrid hash join historically performs magnitudes faster than nested loop join. This performance feature is most beneficial when the searched tables contain tens of millions of records. Hybrid hash is only applied when joining two tables and the result is non-scrollable. A non-scrollable cursor always moves sequentially forward in the result table. The hash join predicate must be an equality predicate that involves a non-key column, or the non-key column must be referenced in the arithmetic or built-in function. The combinations supported are both operands are arithmetic or built-in functions. The left operand is a built-in function or arithmetic. The right operand is a built-in function or arithmetic, or neither the left or right operands are built-in functions or arithmetic. In this example, both operands are determined by the substring function. The group by makes the result set non-scrollable. The variety column is not a leading key column of an index, and the operator is equality. The join method is determined at the fetch phase, so if the explain statement were issued before the fetch, the join method would not display as hybrid hash. Therefore, the fetch first is performed before the explain statement. The predicate is displayed as an equijoin predicate, and in this case, there is only one join predicate. Here is an example where the hash join predicate's left operand is the result of an arithmetic expression, T1.C12 plus T1.C4. Optimized for 1000 makes the result set non-scrollable, and column C12 in table T2 is not a leading key column of an index in a table T2. Moving on to the ease of use features. There are two ease of use features. The first removes the exact length restriction for character data types in the select clause of a union or union all statement. The second feature removes the requirement to recompile the SQL statement or drop the stored procedures, triggers, or views that reference the table whose identity restart value is explicitly reset. Before this feature, resetting the restart value of the identity column caused all persistent objects that reference that altered table to be invalidated. Due to the variable length nature of a character string, the exact length restriction made the union-all feature all but unusable for character constants. Removal of this restriction increases functionality, processing speed, and ease of use. Here is an example of a union between two different tables. Before this feature, this operation would only be allowed if the size of the max price column in the customers table is defined as the same size as the price column in table houses, and the size of the desired loc column in customers is defined as the same size as the location column in table houses. Additionally, the second union previously required the size of the column location be equal to the size of the character constant unknown, which is 7 ASCII character values. The description of this cursor P1 will return the maximum size for each item in the union select statement. For example, RDMS compares the size of the desired loc from table customers with the size of the column location from table houses with the size of the character constant unknown to determine the maximum size of the character value returned for the second item returned in the cursor P1's record. The second ease of use feature is to remove the requirement to recompile the SQL statement or drop the stored procedures, triggers, or views that reference the table whose identity restart value is explicitly reset. Before this feature, resetting the restart value of the identity column caused all persistent objects that reference the altered table to be invalidated. They would, in the case of views, be implicitly dropped, or in the case of stored procedures and triggers, need to be explicitly dropped by the user. In addition, any embedded SQL programs that reference the altered table would need to be recompiled or activate an internal auto recompile. What is an identity value? What is meant by an identity restart value? Identity is a property given to a column on the create table statement. Identity columns are used for generating key values. The identity property on a column guarantees the following. Each new value is generated based on the current seed and increment, and each new value for a particular transaction is different from other concurrent transactions on the table. In this example, the first identity column value generated on insert is 10,000. The increment is not specified, so the default is 1, which means the next insert will be 10,001. When the value of 40,000 is reached, the identity value cycles back to 10,000. This example demonstrates how a user explicitly sets the restart value using the alter table statement. Before this feature, resetting the restart value of the identity column caused all persistent objects that reference the altered table to be invalidated. Now the explicit cycle and the implicit cycle are consistent in their behavior. The last category of features is scalability. There is one feature to increase the limit of 510 file names in a thread. The total number of versions of all tables that can be referenced is now approximately 4,096. This value can grow larger due to internal logic in UDS control. When the 4,096 limit is reached, UDSC will attempt to add free some of the files currently assigned to the application group, allowing more than 4,096 files to be assigned. However, if none of the files can be freed, 4,096 becomes a hard limit and an error is issued.
Unisys offers a comprehensive set of ClearPath Forward services to enrich the value of your ClearPath Forward applications, data, and systems. Please contact your Unisys representative for more information.